All right, so we're now on chapter 14. Chapter 14 is the first chapter in the content for our second exam. And this chapter is all about chemical kinetics. In other words, it's about how fast reactions go. So the speed of the reaction is called the reaction rate, and we're going to look at how we measure the speed of reaction, how we measure reaction rate, and we'll look at what kinds of factors will affect the reaction rate. And the study of this process is what's called chemical kinetics, and that's what we're interested in this chapter. Now, the big prize behind chemical kinetics is going to be that it gives us information about the reaction mechanism. And so that is very, very valuable, and we spend a lot of effort trying to understand reaction mechanisms. Okay, so let's look at let's talk about something that we call the collision model. The collision model basically says that in order for molecules to react, they have to run into each other. They have to collide. If they don't collide, then the bonds can't break. We can't form bonds. So molecules have to run into each other in order to react. We'll find that the more often they run into each other, the faster the reaction is going to be. On top of that, we'll find that the molecules have to have enough energy when they run into each other, and they need to have the correct orientation. If they don't have the correct orientation, then they might not react. So we want to look at four main factors that will affect the rate of a reaction. One is going to be the physical state. We'll talk about solids, liquids, and gases, and homogeneous versus heterogeneous. The second is concentration. The higher the concentration, the faster the reaction. The third thing is going to be the temperature. Almost always, if we increase the temperature, the reaction rate will increase as well. And then finally, the presence of a catalyst. By adding a catalyst, we change the mechanism of a reaction, and the catalyst ends up not being consumed over the course of the reaction. So let's start with the physical state. Again, the collision model tells us that more collisions should give us more reactions. Well, we'll find that gas phase molecules are moving, they are going to be moving more freely and running into each other more often than the liquid phase, so gas phase reactions will go faster than liquid phase reactions. Solid phase reactions go very slowly because the molecules aren't really moving around very much, so they have trouble running into other molecules. Now, certainly they run into the adjacent molecules, but in order for it to react with something else, we would need to move those molecules around. So we'll find that almost always gas phase reactions go faster than liquid, and liquid goes much, much faster than solid. When it comes to homogeneous versus heterogeneous reactions, well, in a homogeneous reaction, the molecules are all in the same phase. So they're more likely to run into each other, and they're more likely to proceed quickly. In a heterogeneous reaction, however, we'll find that they go much slower because the molecules don't run into each other as often. Now, we can speed up the rate of a heterogeneous reaction by increasing the contact area between the phases, but there is a limit to that. So we'll find that if we really want a fast reaction, we're going to do a homogeneous reaction. Our next factor is reactant concentration. Again, generally speaking, increasing the concentration increases the number of collisions. And by increasing the number of collisions, we'll increase the rate of reactions. So an example of this is the steel wool that I have over here on this top picture. It is in air, and since air has a concentration of oxygen at about 21%, we'll find that the reaction goes fairly slowly. So the iron that is in the steel wool will get oxidized, but it goes fairly slowly. If, however, we take that burning piece of steel wool and plunge it into pure oxygen, the reaction rate will go much, much faster and burn much more vigorously. So that's always a fun experiment. All right, so now for reaction temperature. Generally speaking, if we increase the temperature, we will increase the rate of the reaction. The reason behind this is that at higher temperatures, the molecules move faster, and therefore they run into each other more often. And when they run into each other more often, they also have greater energy. So increasing the temperature is a surefire way to increase the rate of reaction. And then finally, our fourth factor is the presence of a catalyst. Catalyst will speed up the rate of the reaction by changing the mechanism. Now, catalysts are kind of special, and they do some really cool stuff. So we're going to look at that in more detail at the end of the chapter. But one of the key features of a catalyst is that a catalyst is not consumed over the course of a reaction. All right. Well, before I can show you how these things affect the rate of reaction, in particular, we're going to spend a lot of time today talking about how concentration affects the rate of reaction. But before we can really dig into that, we have to know how to measure the rate of reaction. And that's going to be our primary goal here today. So the rate of reaction can be determined by monitoring the change in concentration, of the reactants or the products, if we want to, as a function of time. So here we've got the reaction where A is getting converted into B. You'll notice that at 0 seconds we've got 1.00 molecules or moles of A and no moles of B. After 20 seconds, we've got 0.54 moles of A and 0.46 moles of B. And after 40 seconds, it's down to 0.30 moles of A and 0.70 moles of B. So you'll see that the A is decreasing and that the B is increasing. Now, I want you to give me an estimate of how many moles of A do you think there will be at 60 seconds. So I'm going to pause, or I want you to pause the video and make your best estimate of what you think the number of moles of A is going to be at 60 seconds. All right, so now that you've had a chance to look, to give yourself an estimate of the number of moles of A at 60 seconds, let me show you what I came up with. So between 0 seconds and 20 seconds, we will find that the number of moles of A went down by 46%. And if we do the calculation what percentage it goes down between 20 and 40 seconds, we'll see that it goes down by about 44%. We can do that. If we take the amount of change divided by the original amount, so we'll do 0.24 divided by 0.54, and I'm going to switch over to my camera here that's got my calculator. All right, so there I've got my calculator. We'll turn that on. All right, so now that I've got my calculator turned on, we'll do that calculation. We'll take 0.24 and divide that by 0.54. Then we'll multiply that by 100 to make it a percentage. You'll see the number there is about 44%. The first number was 46%. So we're going to say it averages to about 45%. So let's go back to this picture. So here it went down by 46, there it went down by 44. So let's say that on average it goes down by about 45%. Well, we're going to subtract 45% from that number, from the 0.30. So we'll go back to the calculator, and since we're subtracting 45%, let's just multiply it by 55%, and that will give us the value. So 30 times 0.55, and that gives us 16.5. So if you had guessed either 16 or 17 or 0.16 or 0.1 0.16 or 0.17 moles of A. I should have made that 0.30 times 0.55. So if you gotten 0.16 or 0.17 moles of A, good job. All right. So now we want to look at a real chemical reaction. Instead of having A getting converted into B, we want to look at a real chemical reaction. And in this real chemical reaction, we've got butyl chloride that is getting converted that is reacting with water and getting converted into butyl alcohol plus HCl. So in this reaction, whoever did the experiment has measured butyl chloride as a function of time. So they picked out several different times and measured the butyl chloride at those times. Now, on this table, I want to point out something. You'll notice here that we've got square brackets around the C4H9Cl, the butyl chloride. Well, those square brackets, by convention, mean concentration in molarity. So they mean concentration in molarity. So we're going to use that convention throughout the rest of this course. So I wanted to point it out and make a big deal about it. When it comes to calculating the rate of a reaction, we can use the following equation. So the rate of reaction is going to be delta, and of course you guys remember that delta means change. So the change in concentration of butyl chloride over the change in time. Now, you'll notice that I put a negative in front of this. And the reason for that is if we just do change in concentration over change in time, because the concentration is decreasing, we would get a negative value. Well, we want positive values for the rate of reactions. So we simply put a negative out front to make that a positive value. When we're talking about products on the other hand are going to increase in concentration, so we don't need a negative value in front of those. So let's do the calculation for the change in concentration of butyl chloride over the change in time. So I've got the data here. Here's our formula. And we're just going to pick between 0 and 50 seconds to start with. So between 0 and 50 seconds, so here is the concentration at 50 seconds, which I put right there. There's the negative we have out front. We have 0.1000 is right there. And then we'll do 50 seconds minus 100 seconds down in the denominator. Well, if you punch that in your calculator, which I encourage you to do, you will get this value. 1.90 times 10 to the negative 4 molar per second. Now, throughout this chapter, and anytime we're talking about reaction rates, these will be our units for reaction rates, will be molar per second. So molar per second. So you'll see that we've done that calculation, and we could do all of these. We could do the calculation between 50 and 100, 100 and 150, and I've gone ahead and done those and put those values here. So here's that one that we just did, but we can also do between 50 and 100, and we'll see that it's 1.7 times 10 to the negative 4. Between 100 and 150, we get 1.58, so on and so forth. Well, we're going to do this same thing. I do want to point out that the rate of reaction does decrease as time goes on. And we're going to see that happens in just about every single reaction that we look at. So we're going to go over to the in-class assignment and do number 13. All right. So we have a reaction here where A is getting converted into B. We start with a flask that has 0.065 moles of A, and a total volume of 100 milliliters. That's 0.1 liters for our calculation purposes. And then here, these data are collected. So at 0.065, 0.051, 0.042, 0.036, 0.031 moles of A. Calculate the number of moles of B at each time in the table, assuming that there are no molecules of B at time 0. So I've gone ahead and I put 0 in here for the moles of B at time 0. And to get these numbers, we simply need to take the difference between where we started and where we ended on where we started and where we ended on the moles of A, because to the extent that any A was used up, it was converted into B. So if we do 0.065 minus 0.051, we're going to get 0.014. And so you can see here 0.065, you can probably do these in your head. 0.065 minus 0.042 is going to give us 0.023. Okay, and then 0.065 minus 0.039 is going to give us 0.029, and then finally 0.065 minus 0.031 gives us 0.034. So we've got the number of moles of B at each of those times. Now you'll also notice that I've calculated the time in seconds. I just took the time in minutes and multiplied by 60 to get each of these numbers. Since that was an easy calculation to do, I went ahead and did that. To get the concentrations, and we're going to need these concentrations before we can do part B. To get those concentrations, we just need to divide by the number of liters. In other words, we need to divide by 0.1000 liters. So I'm going to take 0.065 and divide by 0.1. Now, once I do this one, you're going to see that this is a really easy calculation, that we don't need to really put these all in the calculator. We can just write them down. It's when you divide by 0.1, it's like multiplying by 10. So 0.065 becomes 0.65. 0.051 becomes 0.51. 0.42 molar, 0.36 molar, and 0.31 molar. For the concentration of B, we'll do the same thing. So 0 divided by 0.1, of course, is 0. 0.14, 0.23, 0.36, 29. I wrote down the wrong number there. Easy mistake. So 0.29, and finally 0.34. So those are the concentrations of B at those time intervals. So next, we want to calculate the average rate of disappearance of A for each 10-minute interval. And so to do this, we're going to look at each of these intervals, and we'll start from 0 to 10 minutes. So in that time slot from 0 to 10 minutes, our rate is equal to negative the change in the concentration of A over the change in time. And we want that time to be in seconds. All right, so negative, and we'll do the concentration at 10 minus the concentration at 0. So 0.51 minus 0.65. And then we will divide that by 600 seconds minus 0 seconds. And that gives us a value. All right, so we'll go ahead and put that number in here. So negative parentheses 0.51 minus 0.65, close parentheses, and then we will divide by 600 minus 0, which is just 600. And then that gives us 2.3333 times 10 to the negative 4. We're just going to do two sig figs here and call it 2.3 times 10 to the negative 4 molar per second. All right, so that is our rate for the first 10-minute interval. So now let's do 10 to 20 minutes. All right, so our rate, it's the same formula here. So our rate is negative, let's see, 0.42 minus 0.51 over 1200 seconds minus 600 seconds. All right. So there's a negative parentheses 0.42 minus 0.51 close parentheses, and then 1200 minus 600 is 600, so we'll do divide by 600. And that's going to give us 1.5 times 10 to the negative 4 molar per second. Now, not surprising, you'll see that the rate of reaction went down. That is exactly what we would expect to happen. So now let's do the interval from 20 minutes to 30 minutes. All right, our rate, so negative, we'll do 0.36 minus 0.42, so 0.36 minus 0.42, and then we'll do 1800 minus 1200. Now 1800, I left a 0 off there, so I'll fix that real quick. So minus 1200 seconds. All right, so negative 0.36 minus 0.42, close parentheses, and then we're going to divide that by 600 seconds. Again, 1800 minus 1200 is 600 seconds. And you'll see the number we get there is 1.0 times 10 to the negative 4 molar per second. All right, finally, from 30 to 40 minutes. And here the rate, 0.31, 0.36, so 0.31 minus 0.36, and then 2400 seconds minus 1800 seconds. All right, and so negative 0.31, oh, got to put those parentheses in. So 0.31 minus 0.36. And then we're going to divide by, again, 2400 minus 1800 is 600, so divide by 600. And the number that we get there is 8.3 times 10 to the negative 5 molar per second. All right, so we definitely see that the rate of this reaction decreases as time goes on. We have one more part of this problem that we want to do, and with this one more part of the problem, we want to see, between 10 and 30 minutes, what is the average rate of appearance of B? Well, here the rate is going to look a little bit different. Instead of being negative, it's going to be the positive, the change in the concentration of B over change in time. The reason that it is positive is because it is a product. So at, let's see, from 10 to 30 minutes. So our concentration of B at 30 minutes was 0.29 molar minus at 10 minutes it's 0.14 molar. And then our time was 1800 minus 600. So 1800 seconds minus 600 seconds. And I put the units in here so that you can clearly see that the answer is going to be in molar per second. So 0.29 minus 0.14, so that gives us 0.15. And then we're going to divide that number by 1800 minus 600, which of course is 1200. We could have just punched that in. But you'll see the number that we get there is 1.25. I'm going to go ahead and round that to 2 sig figs and call it 1.3 times 10 to the negative 4 molar per second. All right, so now I have shown you how you can calculate the rate using just raw data like this. Okay. So I did mention that that the rate decreases as time goes on, and so we want to look at what does that mean? Like, what does that mean, and how can we represent that? Well, we can represent that by looking at a graph. We can plot the data. I'm going to go back to that data that we just had. We can plot this data where on the x-axis we put the time, and on the y-axis we put the concentration. And when we do that, we will get this. So here's our x-axis with time. There's our y-axis with the concentration. Here's our y-axis with the concentration. And that's our concentration versus time. Well, there's more information here. First of all, it's a visual representation of what's going on, and it gives us more information. It turns out that we have calculated the slope between 2 points by doing these rate calculations. We calculated the slope between any 2 points. And that tells us what the rate is between any of those 2 points. Now, what's really cool about this is we can even get rate information at points where we didn't make a measurement, as long as we have a very accurate curve here, and if we're capable of drawing a tangent line to any point, then we can get the rate of the reaction at that point, even though we don't have any data, simply by getting the slope of that line. Now, that's a little bit easier said than done when we're doing this on paper, but if you're doing it on a computer, it's not too hard. So we can get the instantaneous rate. Well, when we look at this, we can clearly see that the rate of reaction changes as time goes on. So that means that we need to decide what is the best point along that curve to get the rate. What's the most representative rate for this reaction? And it turns out by getting the instantaneous rate, the tangent line at 0, the instantaneous rate at 0, that is going to give us the initial rate, and that is the value that we're usually the most interested in, is that initial rate of reaction. All right. So later, when we're looking at rate data, we're going to be looking at initial rates. So we are going to be looking at initial rates. All right. So I want to do one more thing here before we stop this video, and that is to look at reaction rates when we have stoichiometries that are not one-to-one. Just to point this out, you'll notice that in this reaction, all of the coefficients in that reaction are 1. So that means writing the rate for these, calculating the rate is really, really easy. However, if the ratio is not 1-to-1, then we can get the rate of the reaction by slightly modifying our equation to look like this. So Again, negative indicates that we have a reactant, positive for the product. But you'll notice that we took the coefficient and took its reciprocal and put it in front of our delta concentration over delta time. And so 1 over 2, 1/3 here for this product. All right. And we can generalize this. We can generalize this using this particular one. So here our coefficients are the lowercase letters and the chemicals are the uppercase letters. And so we can write the rate law, or not the rate law, but we can write the rate of a reaction, again, negative for the reactants, positive for the products, and it's just 1 over the coefficient to give us a normalized value for those rates. So we're going to look at number 17 on the in-class assignment. And this is a relatively easy problem. All right. So for each of the following gas phase reactions, write the reaction rate in terms of both reactants and products using the general rule for stoichiometry. So our general rule for stoichiometry, again, rate is here we've got a reactant, so we're going to put a negative value out front. Since the coefficient is 2, we'll put 1 over 2 delta concentration of N2O over delta T. Here for nitrogen, again, since this one's a product, we're going to leave it as positive, but we do have a 2 there, so we'll put 1/2 the delta concentration of N2 over delta T. And then finally for the oxygen, it's a product, so it's positive, and the coefficient is 1, so here we just need to put delta O2 over delta T. All right, now for this one, we've got nitrogen, hydrogen, and ammonia. So I'll scoot this down a little bit. So the rate is equal to, this one's going to be negative because it's a reactant, so we'll put negative delta N2 over delta T. And then this one's also reactant, but it has a coefficient, so negative 1/3 delta H2 over delta T. And then finally 1/2 delta NH3 over delta T. And so now we've got the reaction rates for these. So I do want you to know how to do that. All right, well, I'm going to stop this video and we'll start up the next video. Talking about how concentration affects the rate.